couple seconds. So everyone, my name's Charles Feddersen. I'm a Principal Group Program Manager in the Azure SQL Data Warehouse team. So I'd like to thank you for coming today. I think we've got a pretty good session to talk about the scalability that we can enable in the data warehouse service. So we're going to show you some examples of how that works. Andrew, do you want to do an introduction?
Yeah, I'm Andrew Brust. I wear a few different hats. One of them involves being a Microsoft BI guy going back about 20 years. I was on the Partner BI Advisory Council for some time. I'm a data platform MVP in RD. I write about big data and analytics for ZDNet, including actually about many of the features that we're going to talk about today. And my company, Blue Badge Insights, works directly with companies in the industry, including Microsoft itself.
Thank you. Okay, so let's make a start. The session's going to be pretty demo-rich. As you can see from the title, we're going to talk a lot about data warehouse and then show how Power BI and some of those capabilities within Power BI can enable you to work very efficiently over very large scales of data. So if you've come past any of the booths in the last couple of days, you would have seen an architecture similar or identical to this. This is how we think about lifting and moving modern analytics solutions into the cloud. Now, it doesn't represent the totality of Microsoft's analytics portfolio. By design, we try to simplify it. But what I wanted to sort of set the expectations of in this session is we're talking very much about the serve and the visualization pillars within this session. There's been some other sessions on ADF. We've got a great booth with tons of demos for the code-free data flows and the data wrangling. But we're going to focus on the right-hand side of this slide as you look at it here.
And I'll just say Power BI is often thought to be a self-service BI tool, and that's true. But self-service doesn't mean you're all the time hitting CSV and spreadsheet files on your hard disk. Sure. In an enterprise environment, it really means you've got to hit centrally governed data on a really fast platform. And these worlds need to come together, and that's what this whole session's about, really.
That's right. That's right. No, you're right. So, when we think about the data warehouse platform, there are really five pillars that we think about and where we focus our engineering efforts. The first is we believe today that within cloud data warehouses, SQL Data Warehouse is an industry leader or the industry leader on a price performance basis. And this has been validated recently through some independent research by a company called GigaOM on both the TPC-H and TPC-DS benchmarks. People go back and forth about which one's the more relevant to their workload. SQL Data Warehouse leads the market in both of these. We also have a very complete set of security, and this is an enduring investment. As customers are bringing more and more data into the cloud, centralizing larger data sets, then democratizing it to more people, we need a really, really robust security that's also really fine-grained, and we'll just touch on that a little bit in this session to show you those capabilities. We've recently announced a lot of workload management features. The cloud is incredibly powerful for letting you scale out, and that's great if you need more resource. But we've built some capabilities that we think of as effectively scaling in and doing higher value work sooner and having the engine manage that for you so you can get the biggest bang for your buck on a very, very predictable cost basis. For data flexibility, at Build, we announced the ability to query JSON natively in the platform. We'll just take a quick look at that as well. And then developer productivity, for those of you who don't know, we're going to be making SSDT a first class, or SQL Data Warehouse a first class citizen within SSDT, and I'll just give you a glimpse of that if you're not already in the preview. Let me talk about Power BI.
Yeah, and we'll go into more detail on this when we get to the demos. In fact, I don't want to too much step on punchlines here. But for a long time, we've thought about BI as a technology where you pull the data in, where you move the data. And that's still a valid model when you have that luxury. But with today's environment where the number of data sources is increasing and the volume of data is increasing, you can't really do that a lot of the time. So Power BI also has a model called Direct Query that lets you just pull in the schema, build a semantic model, and then query the data in the remote data store in real time. That's good too. However, that creates a kind of a severe choice. Sometimes, actually, you want to blend the two approaches. And a feature that's fairly new to Power BI, composite models and aggregation tables, make that possible. We'll have a demo that makes that real clear. And just to be clear, the database that we're hitting today is not a little 1 gig database off a hard drive on one of these laptops. We're not just talking about petabyte scale. We're actually hitting a petabyte database.
That's correct. That's correct. So I just talked about these 5, and the demos and the talk track today will primarily focus on the left-hand side, how we achieve this performance at scale. But I do just want to spend a little bit of time running over the capabilities in the other 4 pillars, just to make you aware in case you may have missed some of the announcements that we've had at Build here. So first of all, with respect to security, we think of this in 5 layers. Everything from proactive threat protection at the bottom, reading up to data protection. And there's a couple of key points that I'd like to call out here. With respect to access control, SQL Data Warehouse now enables native row-level security. We've had it in SQL Server for a little while. And what this means is, and I go back to that theme of democratizing data that I talked about, as developers or as administrators of these platforms, there will be users who bring applications to bear that you may not actually be aware of. And controlling fine-grained security at the application layer is fundamentally impossible to guarantee. And so with row-level security, and you can also see 2 rows down, column-level security, SQL Data Warehouse in-engine on a per-user basis effectively enables you to secure data at the cell level of an individual table, but the user does not know what they don't know. They just run queries, and we will honor that security policy at runtime. And then at Build, we also announced the private preview of dynamic data masking, another capability that we've had in SQL. For where you have that sensitive data that may be more sensitive to one person than another, we apply masking at runtime as well so that they can't see the true value. Scroll down a little further, you can see support for Active Directory, of course, and then the threat protection. These 3, threat protection, SQL auditing, and vulnerability assessments, these are common across the SQL family in Azure. But what they do is provide 24/7 proactive services that are looking for DDoSes or brute force attacks and shutting those down to protect the platform. And so the full set of features here, we believe, are the most comprehensive set of security features in the cloud data warehouse industry today, and why a lot of customers are looking at SQL Data Warehouse as being that secure repository for some of their most sensitive data. With respect to workload management, we GA'd at Build workload importance. The challenge with workloads before was that, and the way that we handled them was it was on a first-in, first-out basis. And so here you can see we've got the CEO who's sitting at query 12. We classify the CEO's workload as probably the most important query that we need to run. But on a first-in, first-out basis, we handle queries 9, 10, and 11 first because that was the order they arrived in. And so the CEO gets a very, I say, dissatisfying experience, or at best maybe an inconsistent experience, depending on how much pressure was on the platform at the time of running their reports. With workload management, and you can see we've added some syntax here for the workload classifier, you can now set on a per user, group, application, or even a specific tag in an individual query the relative importance of that workload. And so in this scenario, we'll go and set the CEO as high importance. And so when that query arrives, regardless of everything else that's on the platform, we will skip that to the front of the queue and execute immediately. So the predictability of that experience, pushing that high-value work straight into the engine, is guaranteed now, regardless of the demands putting on the platform. It's a simple capability, but we think of this as one of those scale-in type features that let you do more with less and maintain a very, very predictable cost of the platform without constantly scaling out to achieve more and more throughput.
And as a running theme here, like if the CEO is using Power BI and bringing up her dashboard, she will get that priority without having to think about it. That's the running theme, is that there's all kinds of features that can be designed into the warehouse.
That's right.
And then the self-service BI user or the executive BI user or even the more power user BI user is going to benefit from those features almost passively.
Exactly.
We'll show that too.
The key here is they don't need to know, right? And you'll see that in themes of some of the other performance capabilities you talk about. The moment you start asking a broad population, 1,000 users of BI users, to remember this and this if they want to run fast, the whole model breaks down. And so you'll see that through the session. I mentioned JSON. Easiest way to get ahead of this is the same functionality that exists in SQL today. So we shipped this in SQL 2016, I think it was. It's a set of functions within the SQL language. So you can now store JSON documents in the data warehouse, query them natively in their JSON format. It's very useful for if you've got IoT scenarios where you're streaming complex nested types and you want to put them into the warehouse without flattening them first. We've announced a private preview for that at Build as well. I mentioned dynamic data masking. This is another feature that we lift from SQL Server. We're quite fortunate in the data warehouse team that we can lift a lot of very mature, enterprise tested features from that engine into the data warehouse platform. But what dynamic data masking does is, as I mentioned, at runtime, it will determine if the user should have that data masked and then hide it when it returns it to the BI tool.
And with data protection regulations becoming more common, it started in Europe with the general data protection regulation, and it's continuing in California, and it's looking like there's going to be federal legislation on this.
Yep.
That kind of data masking at the repository level, super important to doing analytics and doing it in a way that's legally compliant.
It's a really good point. It's actually interesting. I post a lot of our announcements to LinkedIn, and I see how many views each of those get. I love the performance. I think the performance is cool, just going faster and faster and faster. What was interesting is when I posted some of our recent performance data, it got whatever number of hits it did. The security, when we announced the data classification feature in SQL Data Warehouse, that actually seemed to go viral, that it got 2x the number of views of any of our performance. So we're definitely seeing sort of incidentally that security is absolutely top of mind, and that's why we're going to continue to invest in making Data Warehouse the most secure data warehouse platform in the cloud. So the way that we wanted to go and apply some of our demos today is try and tie them back to some scenarios, right? So if you think about how classical sort of analytics scenarios, these are super generic, right? And it really will focus on the code and how we run these at scale. But we're really going to look at 6 scenarios. We're going to look at period-on-period sales performance, product-specific performance, orders by geographic, et cetera, et cetera. And we'll run through each 6 of these, not so much to say, hey, this is how you should do this query, but here's an example of achieving this, and this is why the capabilities within SQL Data Warehouse make this highly efficient at the scale that we're running. So what does this petabyte look like? We're going to use the TPCH dataset, because that's what we have handy, and the line item table that we will touch today has 6 trillion records in it.
Trillion with a T.
That's right, with a T.
Just
The interesting thing about this data set is I will tell you that I think it is probably unrealistic. And the reason I will tell you that is for customers whom we speak to have multi-terabyte, multi-petabyte workloads and are working with us to look at offloading some of those legacy appliance workloads, large-scale legacy appliance workloads into the cloud, they don't have 8 tables. They have 10,000 tables. And so the size of these tables is probably disproportionately large. But certainly we see scenarios where customers have 1 or 2 very large fact tables, but their dimensions are typically smaller. But this is the data set that we will be banging on today with DW. So how do we achieve this performance? And again, there's some features in here that we've announced private preview for build. First of all, SQL Data Warehouse is a fully elastic cloud architecture. We separate compute from storage entirely, so you can pause and resume the cluster, you can scale it up, and you can scale it down. Columnar storage is pretty much table stakes. Industry has, I'd say almost every analytics platform now depends on some format of columnar. In the big data ecosystem, I think Parquet and ORC have been the 2 predominant. I think Parquet is getting a little bit more airtime these days. But SQL Data Warehouse defaults to a columnar optimized format. At Build, we announced the private preview of ordered columnar store. And so what this enables you to do is order within your columnar store table at the time that you insert that table or build that table, you can explicitly define now a key to order on. And that gives significant optimization to your segment elimination when you're doing a predicate or a where clause on that filter. And I'll show you an example of that working today. Table partitioning is table stakes as well. Pretty much every or any platform supports table partitioning today. It's another capability of just pruning away excess amounts of data. Typically, you can automate it pretty easily just by partitioning on time, and month is a common one. And we're going to partition today and show you how that works. This is something that SQL shipped almost 15 years ago. I can't believe it's been that long. One of the unique features around Data Warehouse is we also let you create non-clustered indexes on top of columnar indexes. So if you've run SQL Server before, non-clustered indexes are a B-tree format, and they enable you to find effectively a needle in a haystack. And so if you remember back to that previous slide that I had on the petabyte, the customer table here has 150 billion records in it. Keep that in mind, because I'm going to show you what kind of performance we can get for finding a single record out of 150 billion. And we're seeing this is actually a relatively common sort of hybrid approach in warehousing, where customers are not only looking to aggregate and scan 1 billion records, but also seek a single record directly out of a large table.
But to be clear, most data warehouses are much better at the aggregation than they are at those point lookups. So this is a big deal. We're making it look easy here, or your team is, but this is a big deal that we can kind of do both workloads in one place.
Yep. We announced the private preview of materialized views. What materialized views do is effectively let you define a view with a select statement. We let you join in that select statement. We're the only cloud data warehouse that enables you to join tables in a materialized view. And the smarts of this feature, similar to SQL, is that we do automatic matching against the optimizer. And I'll show you how, when I run a query against a set of tables, the distributed optimizer in Data Warehouse will automatically match that to a materialized view because it determines it can solve the query correctly through a much cheaper route. And that's another one of these scenarios where we're not going to be asking users to say, hey, query this view for this and query that view for that. Users are really good at saying, okay, here are my tables, and I can write SQL. The optimizer will handle everything else to give them the fastest response time possible. And then result set caching as well, we announced as a private preview. Really simple feature that effectively, if we see exactly the same query on unchanged data, we'll go hit a cache and we return a result set in about 0.2 seconds. So we're going to drill into each of these, but this set of 8 capabilities is unique in the market today, and it's this set that really enables us to deliver performant analytics on a petabyte scale warehouse. And I should actually footnote, although we're not going to show it, through building this demo, we actually spun off a couple of tables, and we ended up actually in excess of 2 petabytes in the platform. We're not going to touch all of it. The point being, as you can see on the next slide, that our storage is actually infinite. The official statement for columnar storage in Data Warehouse is that it's bottomless. So if you're sitting there and saying, hold on, I've got 50 petabytes, that's fine. We can put that in as well. I haven't found many yet, though.
It doesn't come up a lot, although people may brag about the size of their warehouse being
That's right.
50 petabytes, but yeah.
So with respect to scalability, the scale that we're going to run on today is in excess of 4,000 cores. Right? This is the Elastic platform. You can scale it down to single-digit cores as well, but we've dialed it up for this workload today. We built in the second generation of the service what we call an adaptive cache. It's an NVMe SSD-backed cache that when you move data off the shared cloud storage up into the cluster, we'll fill the column store object pool first, and then we'll fill a bunch of SSDs which are local to the machine. And then we have cache eviction policies to keep the hottest data in memory, not quite as hot, but used on the SSDs. And then once they get full, we evict the least used data out of that cache. And so this is one of the capabilities that gives us the performance. And at the scale that we're running today, the aggregate I/O from that SSD back cache is about 720 gigabytes per second.
And that's another sort of blending. Out there on the market, there's a notable competitor that uses SSDs exclusively. There's another competitor that uses object storage in the cloud exclusively. You guys have kind of given us the best of both.
Yep. It's, we try.
Yeah. Appreciate that.
And so infinite storage I touched on, and then I talked about the elasticity of the service as well. When I talk about elasticity, you can scale this up and down in a matter of minutes. Okay, so we see customers who are actually adjusting the footprint or the topology of the cluster on a daily basis. One thing I've not mentioned here, but I'll just call it out, is a couple of months ago, about 6 weeks ago actually, we actually announced reserve discounts for the platform as well. 1 and 3 year pre-commits gives you the discount in line with other 1 and 3 year pre-commits of other services. The thing that I want to call out about that is the capacity you reserve does not break the elasticity model of the platform. And so what a lot of customers who are in production today have determined, okay, I've sort of got a foundational capacity that I run on at any time of the day, and then sometimes I burst up and down. So what they actually do is they reserve the foundational scope that they run on, maybe 2,000 or 3,000 DWUs, and whenever they burst up, they just pay the on-demand rate for the delta. So it's publicly documented today, you can take a look at it, but some of our customers have realized significant savings by just reserving a base capacity that they're running at 24/7. So with respect to the Elastic architecture, I won't spend too much time on this. The core here is the separation of compute and storage. We see a lot of customers who run their warehouses during the week and just hit pause on the weekend. Your data is completely safe. It is triplicate in Azure storage, and if you enable it, we will do geo-redundant backup as well onto a secondary data center. So we store that on cloud storage, and it's available. With respect to how column store works, and if you've touched SQL Server dating back to 2012, you'd have a pretty good idea of this. Columnar storage effectively breaks the data up into row groups of about 1 million rows, which we represent by the horizontal boxes here, and then breaks that into columns. We typically see about 5x compression in column store, because once you compress only values of a single type, replication is typically higher because the type of the data type limits the different values you can have. And we've seen about 5x in the demo we're going to show you today. And so in this example, you can see if I just ask for customer key where the value is greater than 120,000. You can see here that the blue boxes are the only two segments that I've read. And this is a common theme. You'll see this graphic in the next few slides, basically showing that although we can bring 4,000 cores and we can bring really high SSD scan rates, the secret of operating over data at scale is being able to prune away as much data as you possibly can. And it's that collection of structures, indexing, column store, ordering, true table partitioning, that gives you the ability to really funnel and prune away any excess data and just work on the minimum that you need to resolve a query.
And to be clear, columnar storage is a technology that makes its way into the data warehousing world, into the BI world, and also into the big data world with Hadoop and Spark. These worlds are really all one big world, but they've been kind of artificially separated. A lot of the concepts are coming together here.
That's right. I think, so just to talk about partitioning as well, again, a feature that's existed in SQL Server for a while. When you define a table, you define the partitioning ranges. When you run a query, for example, that looks for a couple of range, I'm asking for the 1st to the 8th of February here, it can ignore all of those partitions. Before it even starts pruning columnar segments, we can just prune away partitions in the table, and then we can start pruning segments after that. So again, very, very efficient at I/O management. What this means when you can prune away huge amounts of data at the actual storage layer is you need to cache less. And if you need to cache less, then you need potentially smaller clusters because you don't need as much cache. So all of these accrue into significant cost savings, aside the fact that we already have the price performance that's been published.
And you'll see partitioning strategies once again, in the BI world, and also, let's say, with Parquet files in the world of Spark. You have to be, in those worlds though, you have to be a little bit more sort of deliberate and aware of how you architect things. I would say in the warehouse world, especially the way Azure Data Warehouse has set it up, again, you can benefit from that a bit more passively.
Sure.
Yep,
absolutely.
We'll see that at work.
So finally, and here's some syntax that you won't have seen in SQL Server. This is where we start to move into the distributed world. In the table definition, we give you the ability to distribute based on hash. We also have round robin and replicate distributions. Really useful if you're sort of moving those Kimball models and dimensions and facts. Replicate hash distribution is a great way to model that. But what this does is effectively scales out your data into physical sort of subsets, so into 60 buckets. Each bucket contains a partial set of your data. And this is where the scale-out cluster does its magic with the distributed optimizer, that to you it looks like a SQL server under your desk. And you just submit SQL queries. Under the covers, we determine exactly how to resolve that query, potentially over a cluster of pretty powerful machines.
To drive that point home completely, all the dashboards we'll show you in Power BI, the connections in Power BI, you actually just pick SQL Server as the database. There's nothing specific for data warehouse.
That's exactly right. Now, we could do that. That's the dirty secret, is SQL Data Warehouse is really highly compatible with SQL Server. If you're using BI tools that don't have a named connector for SQL Data Warehouse, quite often you can just say SQL Server and put in the server name, and it will just work. So here's a quick look at just what we talked about. We talked about, if you take a look at the table definition here, if you've done partitioning in SQL Server, you will have created partition functions, then partition schemes, and then referenced them in the table. We do things a little differently in SQL Data Warehouse. In this platform, everything is defined in the table DDL itself. So cluster column store index, we put the partition range directly in the DDL. We don't worry about having to create partition functions and schemes. And then we have this concept of distribution, which is how we can shard the data out across physicals. So let's switch to demo 1, and I'll show you exactly what that looks.
All right.
7, please.
Lucky 7. And you're on.
Okay, so here you can see I've got exactly what I just had on the last slide. Right? This is sort of a table definition. I've got far more partitions in this table. I just sort of flushed them away just to prove the point here. Now let me show you what we're actually running on here. So I'm going to go run this guy. And what you can see is I have 60 rows. If you can squint down the bottom, that says 60. And this represents the 60 shards. And each of these shows the number of rows that I have for my table. And you can see right here, this number here shows 98 billion records. So for each instance of SQL that I'm running here, I have 60 nodes attached to 60 distributions. I have 98 billion records being queried by being attached to an individual SQL instance. And this is just one table. This is the large table. I've actually got 2 copies of this one, remember? But this is just to show how we break the data apart, and this is a command that you won't have seen in SQL Server previously. So let's go run a query here, and this is where we're talking about period-on-period sales. Let me just move this down. So I'm going to go run this guy. Where is he? Yeah, make sure we're at the bottom here. And so what this is doing is stretching out the capabilities we just talked about. It's asking for a subset of columns, right? We're looking here at the ship date, the extended price. We're filtering on the ship date to prune away those partitions. So we're only touching 2 partitions out of 86, right? And then down below, you can see we're doing a few window aggregates to demonstrate how we can compare 2 periods together. And so this is going to run for fractionally longer, and it's finished in 23 seconds. And I can tell you, I just lifted this number up. This scanned about 147 billion records in 23 seconds. So this is the scale of the performance that we're talking about. And this is actually, I'll just footnote this is using the float data type, which is not our most performant in this scenario. SQL has a deep optimization in the engine that will push down aggregates into the scan if you're using 8-byte types or less. Had I run this with decimal 15.2, it actually would have come back in around about 14 or 15 seconds. I didn't get a chance to set that up before the session. So if I show you actually just what happened here, all right, let me go and just take this. Actually, no. I'm going to show you. I'll show you this actually in the next demo because it's a little bit clearer. Okay, let's flip back to the slides and we'll keep going. So in that one, we touched on column store doing its thing, partitioning, and the scale-out capability, the 60 distribution, the hash distribution of the platform. As you saw, I did nothing. I didn't have to tell it where the distributions were or anything like that. I just sent the SQL query and it figured it out.
And that we scanned what? 147 billion with a B rows in 23 seconds.
Yeah.
That's pretty slick. And we didn't just talk about it on the slide. You actually just did it.
I find proving it actually has a little bit more cred. 30,000. Dialed up, yep. So here's an example of what we announced now at our build for private preview. So when SQL originally shipped column store, we didn't give you the ability to order it. The workaround for this to order your data so that you could actually get a pretty efficient pruning on a single or multiple columns if you ordered by 2 was to create a clustered index and then to build a clustered column store index on top of it with a max stop 1 so that you just ran straight down and got that ordering correct. So now we let you define clustered column store indexes explicitly with ordering, and you can see the syntax right here. And so we're going to release this into public preview in the next month or so. What this means is that if you look back at that previous slide, if you take product key for an example, you'll notice that there's fractional overlap in my min and max ranges that I store in my metadata. So 1 through 2102, 2102 through 5423. But it means that where I predicate on one of those values, I can really efficiently prune these segments away. And so I can now, by ordering is incredibly powerful for optimizing your I/O, and now your columnar index can have an order in it. And so what the other sort of benefit of doing this is, and I can sort of give some numbers here, when I started building this and I had my 6 trillion row table with no partitioning and with no ordering, it was about 237 terabytes on disk. Right, I took a look at it. Once I applied partitioning to it, which naturally arranges similar rows a little closer together, that came down to about 215 terabytes. I actually saved 20 terabytes by having sort of more structure in my data through table partitioning. And then when I ordered it, I started to lower that even further because really similar values were being clustered quite closely together before they were compressed. And I expect actually, I didn't quite look at the finished product, but I'd be very close to about 200 terabytes. So that's almost about a 20% saving on size on disk, which obviously improves I/O, improves your cache efficiency. It's just goodness all around, simply by structuring the data in a pretty uniform way that's going to enable your queries to run significantly faster. So I'm going to flip now to the second demo, and this is actually going to go pick a needle out of a haystack. Can I take number 7, please, sir?
You're on.
So what I'm going to go do here, you can see I've got an example of what I'm operating over here. So I've ordered by part key. I could order by additional columns if you want, but here I've ordered this table by part key. It's also partitioned already. So now what I'm going to go do is I'm going to run this guy, And you can see here I'm looking for a few other columns. Quantity, extended price, discount tax, fine. Here's my table. I'm looking at a 6-month range, but I'm looking for it's a big needle in this haystack, right? I'm looking for everything where this part key has been used. And so let me go run this guy now. I expect this to be pretty snappy. 1 second. So this is, I'm not going to lie, this is coming off a relatively warm cache, I would suggest. But what this query has gone and done now is actually aggregated over, I had the number, I think I've lost it, about 350 billion records, but it's hardly had to touch any of them. Because I've ordered my data by that part key and I have table partitioning, this table that has 86 partitions, I just immediately threw 80 of them away before I ran the query. And then I looked at a very ordered, sometimes referred to as clustering, we call it ordering key. And then I've been able to find just those row group segments, and then I've been able to read across to the subsequent columns very efficiently. So we've touched a number of columns, but with ordering, we were able to find our entry point onto the rows we needed incredibly efficiently. And that's what gives us this level of performance.
And that's sort of the secret of big data is you have huge volumes. The way you sort of solve that is not through magic, but by divide and conquer through parallel operations and through just kind of common sense triaging.
That's right.
And all those things are getting combined here.
So I'm glad you brought up parallelizing. What I've gone and done is I've just pulled the request ID from that query that I ran, and I want to show you what actually happened under the covers here to achieve this level of performance. So first of all, I'm going to go and grab the steps. And you can see here, this is what a distributed plan looks like. So we did a couple of things here. I'm sorry it's a little small. Return ID. The main thing to look at here is we did a small shuffle, but this is the distributed plan that came back in about 2 seconds. But what I'm going to do now is I'm going to drill into this. And this is the second step, which was the shuffle move. And what you can see here is there are 60 rows again. So what the distributed optimizer has done is said, okay, I see your query. I've got the data spread across 60 buckets attached to 60 instances of SQL. So I need to go issue 60 queries, one to each of those SQL instances to do its work. And then I'm going to need to re-aggregate that to provide the final result set. And so if you actually drill in, you can see the actual SQL command that was sent down to the platform. And I can sort of give you a hint of the scale here because we explicitly send down, where is it here? It's a little further. There it is. It's a little small. You can see that we maxed op 72 right there, about where my mouse is. So each of these machines with 72 cores has been sent this query to operate at this scale, and that's the scale of the platform that we're working at. And so if you do a quick little bit of maths in your head, which you can probably figure out, 60 machines running, 72 cores each, about 4,320 cores that are running over this data. So it's very scalable, but at any point I could, of course, pull this back again through low periods if I didn't need this level of performance. We find that a little more capacity in the demo helps us move a little faster. No one wants to sit in an audience and watch 4-second or 8 seconds demos, of course. Back to the slides, please, sir.
You're there.
Okay. So that's sort of the basics of columnar ordering, partitioning, and hash distribution. Now let's talk about what we've recently introduced with materialized views. And so we've had materialized views in SQL Server for a little while, and they behaved in a very similar way, except for the fact that they did not have the distribution equals hash, which is one of the properties of a distributed system. What the materialized view does is lets me run this query, for example, and it will materialize the result set of this in a columnar format, so it's hyper-optimized, but we will store it hash distributed on this product key. And this becomes really important if you have complex queries that have a whole lot of joins. And so I'm going to try and walk through a scenario here and describe the value and the benefits you get from materialized views. Joining maybe a set of tables together, and then the optimizer will automatically match them. The important thing to note here, remember, is that materialized views have maintained transactionally consistency to any modifications in the data. And so if I add records or update records, we will update the materialized view immediately, so you don't need to rebuild it, and it is not a full rebuild process. Sometimes actually materializing a view can be relatively heavy operation. This one took a few hours when I was setting up the demo, but that's a few hours that's saved in query execution at this scale. So if you take a look here, and I hope this text is large enough, I'm creating a materialized view between a fact sales table. This text is not indicative of what we're using today, with 10 billion records and the DIM product table of 1,000 records. So I've created this join, and this is going to produce a table. If a user then walks up and runs a query, it'll determine that the definition of my view matches the query that they're running. And I'll show you shortly that it does not need to be character for character identical, but just for the sake of this illustration, I've left them identical. And so what will happen is this query at the bottom will run, and it'll join fact inventory to the materialized view, even though the user's query said fact sales and DIM product in purple text. So this is the optimizer determining that, okay, they've asked to join these tables, and these are the columns and level of aggregation that was required. I already have that stored in a materialized view, so I'm going to rewrite that query and just match this fact inventory table directly to the product sales. And so consider a scenario where that materialized view in the top section took 10 minutes to build, but then 1 second to query. Every time you come and run that query, what would have been 10 minutes every single execution, the optimizer will just bring that down to a couple of seconds every time, and we'll show you that shortly. So I'm going to walk through an example using this query, and this goes and joins the month partition with orders with customer. And in a distributed system, this is a tricky-ish query. It's not uncommon. In SQL Server, it's pretty easy because everything's in one box. There's no notion of distribution. But in a distributed platform where we physically separate the data, we need a way to move data, and that's where things can get a little expensive. So in this scenario, as I had here, the month partition table is distributed on the order key. The orders table is distributed on the order key. And then the customer table is distributed on the customer key. That's just something to remember, but just keep it in mind for a second. What happens then when I run this query? So you can see the blue box's order key on both sides are both my distribution keys. And when I distribute data, that's a deterministic algorithm that means that a value from one side will match a value from another table in a node. And the optimizer understands that, and it can co-locate that join in the physical machine. But then if I ask to go and join on customer key and customer key from orders and customer, that's where it breaks down, because there's no guarantee as to where those customer keys in the order table are located, because that's not my distribution key. And so the result of this is going to be that this stage will run first, and then what's going to happen is a shuffle will be required to produce a temporary table of orders plus line item, the columns that I needed, and then we will co-locate that join. Shuffles, at this point, I'll point out, are not bad, right? Shuffles are a mandatory part of any distributed system. The trick is to minimize the shuffles, both the volume of rows that you're moving, or nullify the fact that it may need to occur at all through the way that you model your data. And so in this scenario, this would be relatively expensive because these are very large tables. I've got 6 trillion records on the right and 1.5 trillion 6 trillion in line item and 1.5 trillion in orders. And so this is going to be an expensive join, right? Just period, for any platform. And so what we can go do here is create a materialized view that takes the work out of this. And so, let me go back. So the first thing to notice here, midway down, is that I'm taking my line item table and my orders table, and I'm joining them on the keys that I require. I'm pulling the columns that I require. But the output of this materialized view in the second row is going to hash on the customer key. So now I've got the output of that expensive join, and I've persisted the results of it, but I've stored it distributed on the key that aligns with subsequent joins that I'm frequently making, perhaps to the customer table. And so in this scenario now, the exact same query run by the user is not going to go and touch those tables at all. It's going to go and reference the materialized view. It's going to determine that it's got a perfectly co-located set of joins across 3 tables, and this is just going to go run and bring back a result set. In this example, actually not this exact example, but an example that I built separately, the benefit of materialized views was to reduce a query from almost 5 minutes down to 5 seconds of execution time. I've seen more dramatic improvements as well. I've seen some less as well. But this is the magnitude of the saving. And again, remember, coming back to highly concurrent workloads, a lot of users running complex queries, the magnitude of this saving is significant and can potentially, again, enable you to reduce the amount of capacity you need to run really large workloads because the engine is doing so much optimization for you, and we're structuring and storing our data in a really, really powerful way. So having joins as part of these materialized views is an absolutely critical capability that we've private previewed, as we mentioned, at Build. So sort of to belabor this before we go into the demo, I've sort of got an illustration here. It's a very simple illustration as we start to get into more of the Power BI stuff. The critical thing here is when the user's coming from Power BI, they don't necessarily see what a materialized view is. In fact, I can guarantee you that Power BI does not have an icon or any iconography to say this is a materialized view versus a normal view, right? They need to trust that if they go query the tables they need, the platform will honor that optimization. And so the simple decision that you're going to see here is an optimizer making decision as whether I hit a table or whether I go hit the materialized view. So let's go take a quick demo here, and then we'll start to look at some of the Power BI. So here I'm in another demo 3, and I'm not going to run this. I've already run this to set it up, but I just want to show you, ignore the fact that materialized up here is black. It's because I don't have a version of the tooling yet that turns the text blue, but shortly we will, so make sure you keep everything up to date here. And so I've said here, I've got a date, and I wanted to explicitly put this in. I've got a greater than or equal to date, and that's going to become important shortly. So let me go down here, and if I ran this query without a materialized view, I'm just going to show you what the plan here looks like. And this is going to be a little small, I'm sorry. But I ran a query that joins line item, month partition, and orders. They were the tables. What I should expect here is line item and orders getting joined somewhere, and then returning the aggregate result set. But what you'll actually see, and it's incredibly small, is MVW customer sales. So the plan that it's generated has said, no, you've got a materialized view that you can just go hit. And so when I come down and look at something a little further down, you can see that I've got this query here. And now there's a couple of things that I want to call out here. First of all, I've taken some columns out of my materialized view definition, so it's not text exact. If I show you down here, I'm also not filtering on greater than or equal to that date. I'm looking for an equality of a date directly within that range that I set. Yet I can go run this again and give you a plan. And what you'll see here is I'm joining customer, nation, and region. Let's just lift this up a little bit here. So this is going to be region, this is going to be nation, and this is going to be customer. But up here, I'm hitting my materialized view again. So the purpose of this demo is to show that even though I'm changing the definition, it's not matching text for text exact. It's determining that the materialized view has sufficient fidelity of the data in the aggregation and the columns to resolve this query. And then so when I come and ask for either the exact aggregation and range or a subset of that, it's still going to determine that the materialized view is the optimal. And I can probably go run this quickly just to prove that it goes pretty quick, I hope. We've had a good run so far. And so we'll let this guy go run, and I expect this is going to come back relatively quickly, leveraging that materialized view.
It's done.
Okay? It's done. There you go. So what this has done is gone all the way from the line item, joining through orders, joining through customer, through nation, through region, to a really high-level aggregation in the platform. But that really expensive join that I don't want to do every time has been completely nullified because I have a materialized view that represents that, and the optimizer just figures it out. So again, you think about it from a Power BI standpoint, when I'm dragging and dropping things around, DW is doing all the heavy lifting to give you that performance.
Speaking of which, should we
show us some Power BI, sir?
A quick dashboard here. So here we've got the order count by region for Middle East, Africa, and Asia. And I actually brought this up already because I didn't want you guys to have to sit through the Power BI splash screen. But to make this honest, let's go ahead and just hit the refresh button on this. First, the model gets refreshed, and then I'll zoom in. While you see that spinner spinning, that means that the query is rerunning. And what you should see, it certainly worked in rehearsal, is that we're done in about 5 seconds. So certainly not exactly the same as running local, but we're talking about billions and trillions of rows here. And I actually hit a view, but it wasn't your materialized view, right? It was a view on top of it.
That's
and
right.
It knew, or on top of the table, and it knew when to hit the materialized view to come in here.
It's actually a really good point. What we see a lot of customers doing to help simplify the way that their data is presented to users, particularly through tools such as Power BI, is create sort of that semantic layer of views on top of it, and the users just access the views. The view that Andrew hit sat on top of a materialized view. So that level of compatibility exists, that you can have regular non-materialized views sitting on top of materialized views on top of tables. Optimizer will figure everything out.
All right, great. And now let's talk a little bit about these features in Power BI. I can use the keyboard, we're good. That sort of merge the worlds of BI and big data. The problem is these have been different worlds because BI tools don't really deal in petabyte scale stuff. And while you can take a BI tool and connect it directly to something like Spark SQL or Hive, or for that matter, a data warehouse that's at petabyte scale, while you can do that, you really have to kind of fudge things and get into small subsets of data for that to work. So for the import approach, where everything goes in memory, you're going to need to do data movement. And that's, in many cases, not going to be efficient. It's not going to be feasible, certainly if we're talking about petabyte scale databases. And it's also going to introduce latency because you're going to need to refresh your local model from the remote data. So the other option, and again, this has been kind of a severe choice, you'll see this with other BI platforms, is, sorry about that, I stepped on my own punchline, Direct Query lets you go and get all the data from the remote data source, and that way the latency and the movement goes away, but you lose out on being able to optimize certain things locally. So the approach that the Power BI team introduced recently was to say you can actually put these two models together in a single model. That gets called a composite model. And as a further kind of fine-tuning on that, what you can also do is take the data that would be in your detailed fact table that's in the remote database and aggregate it at a high level and store that locally. And if you play your cards right, Power BI will understand that if you're asking for a high-level aggregation of the detailed table, that it will go to the local version that's aggregated. And if you ask for something at the detailed level, then it will go ahead and funnel out to the remote and do push down on the query. So what I can show you over here is we have another Power BI model, and I'm going to do a little zooming here. So what we've got, this is the sales detail table. This is basically our detailed fact table. We have an aggregated version of it here, which I've hidden, and it's aggregated by order key and customer key. So this one is local, and to be real clear about that, let me zoom out. Let me show you that it is in fact set to import. Let me zoom out over here. If I go to the detailed one, that is set to direct query. And then for some of our dimensions, our customers and our orders, those are going to get set to dual. So what that means is if I'm doing something at the aggregated level, it'll use a local version of the dimension table. If I do something at the detailed level, it will use the direct query version. And because some things are going to get used in both contexts, we need to be able to set that up as dual. Supplier, on the other hand, is set up as direct query. So supplier is direct query, sales detail is direct query, the aggregate table is local, and these two guys are dual. And when I say local, I mean import. So here we are actually in a dashboard now, and what we're looking at is sales, or the sum of extended price by customer. And this one will come back pretty quickly. It came up in about 3 seconds. We can refresh that. I'm not even going to bore you with that part. But what I am going to tell you is I might want to go down to the supplier level, which if you'll remember, supplier was direct query. I've set up a second page here where we can query the detail by supplier for a particular customer. One cool thing that Power BI lets you do, though, is take that page and actually set it up as a tooltip. So in effect, and I have a couple of these already cached, so that comes up right away. That's giving you the aggregation of extended price by supplier for this particular customer. And I did a couple of these already, so they come up pretty quickly. But let's pick another bar that I hadn't done yet. And now what it's doing is it's actually running a detailed query on the warehouse on the fly, and we've populated a tooltip with that crazy kind of query that normally you would think, oh my gosh, that's going to be a BSTK query. You know what BSTK is? Bring the server to its knees. But that's not what happened here. It came back in just a few seconds. Sure. And I could do it again over here, and you'd get the same result. So with that, I'm going to push it back to the slides for you to tell our next story.
So the next story is around the secondary indexes. I think there's only one other data warehouse platform. It's an appliance form factor that offers secondary indexes. I think it might be Teradata. And secondary indexes are fantastic for finding that needle in a haystack. The problem is it's so fast that I'm actually going to show you how to find lots of needles. But what this enables you to do is you can see I've got a columnar store on the left-hand side as you look at it. And I have this query that says, give me the customer key and the sum of the amount where the customer key equals this number. Right? And so again, what the local optimizer in SQL will do is say, I could resolve this in the column store. I could, but it's going to be cheaper for me to just traverse and seek through a B-tree index, which is incredibly efficient, and find this value and return that. Again, users, like database platforms, users don't need to know what's indexed where, but this capability of creating a B-tree structure on top of a columnar store is incredibly powerful. And this is actually one of the reasons that we're seeing a lot of existing legacy appliances start to move to SQL DW because of the complete feature set that we offer for effectively just lifting and shifting these workloads over. And so let me show you quickly what this looks like. Now it's build, and I should be running some stuff out of Visual Studio, I'm sure, but I just baked this up quickly. And what this is going to go do is just start sending now queries. And so this is asking for an explicit phone number from a table, the customer table of 150 billion records. And so what the B-tree index is able to do, that we have from SQL Server, is find this record comfortably sub-second and return that to the user. Okay? So it's very powerful for that fine-grained search. Now, what I'm going to do actually is just snap this across here, because there's never just one query running. Let's go back to demo 2, for example. I'm just going to pull this guy. Let's go run our real query again. So where's this guy? There he is. And we'll run this guy. And so this query is going to come back 1 second, and you hardly see a blip in the non-clustered index. Because it is such an efficient operation, it has very low memory requirements to go and seek this. We can sit here and bang this query that's operating over 350 billion records of data. It's going to keep coming back in a couple of seconds, and the velocity of our index seeks over here barely misses a beat. And so this is the power of the platform for handling very sort of diverse workloads that are seeking individual records, that are aggregating a billion records comfortably across, as I mentioned, very large user bases who have a diverse set of requirements of the platform. Let's go back to the slides one more time, please, sir. And so finally, at the top of the session, I mentioned result set caching. This is really where things get insanely fast relative to everything that we've shown so far. With result set caching, a user will run a query. We'll capture the text of that query, and when the results come back, we will store them in a cache in the cluster. Two important things about this. First of all, that result set cache is resilient to cluster scaling. So if you have a cluster that you scale multiple times per day, we do not evict that cache when you scale the cluster. And so when that next report comes in, if it sees the exact same query and the underlying data that it depends on is unchanged, it will just hit the result set cache and it will return in about 0.2 seconds. Typically, 0.1 through 0.3 is what I've typically experienced. This is super powerful for, as Andrew mentioned, Power BI offers this direct query mode. And with direct query, you're sending a lot of SQL queries down to the platform. You can have some pretty populated dashboards with lots of widgets sending lots of queries. But dashboards typically are pretty repetitive workloads. And so if we understand the answer to that workload, we'll just cache it. And then when the user comes, they're going to go run it. And so the final demo of the session, if we just switch to Andrew quickly.
We're there?
Yep, just give me 1 second. In
Sure.
fact, so what I'm going to go do is I'm going to turn on the result set cache on my machine. We've had it turned off, by the way, so far, so that the queries we're running didn't come back unrealistically quickly.
I can refresh once before you turn it on if you
No, that's okay.
All
that's
right.
okay. So we're just turning this on right now.
And we're looking at balance by country, balance by region, and orders by week number. And actually balanced by country, we're looking at in both this donut chart and the text cards going across the top here.
And I'll show you the command that I ran in a second. So Andrew, you want to go refresh that quickly?
All right, here we go.
So this will be the first hit, and this won't have seen, the result set cache hasn't seen this. So spin our little circles here. I think this comes back in a few seconds. It's not too bad, regardless.
Right, we're done.
But this is going to come. Now, if you go refresh that again, all of these result sets should have cached. And so pay attention quickly.
Done.
Okay, so that's the power of the result set cache. Now, the moment we go and load more data into any of those tables, that result set cache will be evicted because it would be returning the wrong result potentially. But for scenarios where you're loading maybe once or twice a day, and people are just sending that dashboard down. I spoke to a customer recently who did legitimately have 17 million queries per day. The fact that on a given version of the data between loads, you only need to run one of those queries once, and then subsequent executions will just hit the result set cache, is a massive scalability capability that lets you reduce potentially the amount of compute you need. And you could actually run maybe bigger compute in the morning while all of these are cached up in the result set, and then scale it down. Remember that result set cache is resilient to scaling. And so you could go smaller and know that your user base is primarily going to hit result set caches for the remainder of the day.
That really felt like it was import, but it was truly direct query.
Just to close up here, I want to touch on one thing, which is a question that we commonly get, and I tried to hit it sort of in the main part of the session. The difference between materialized views and result set caching is that result set cache will look at the totality of a single query, character for character. That's how it does its matching in the engine. Result set materialized views will look at either a full query or a subset of a query, and even a derivative of that subset. That was why I showed you the filters where they were exact and I removed some of the columns. So this is the difference between the two. Technically speaking, if you have a materialized view that's like that regions that I had, and you submit that exact same query, it's going to come back just as fast as a result set cache. But this is the difference between the two techs. So in summary, these were sort of the 8 key features of SQL Data Warehouse, the combination of which I mentioned we believe is unique today and gives you an ability to solve for these very, very large workloads that have very different query patterns, which we tried to demonstrate. Columnar and columnar ordering that we just announced to build today. True table partitioning, the ability to set ranges and just prune away vast amounts of the table. Non-clustered indexes, which we showed right at the end with the little command prompt, the ability just to hit individual records out of a 150 billion record table. Hash distribution, we showed splitting into 60 buckets, materialized view matching within your queries, and then the result set cache right at the end for those sub-second dashboards, regardless of how many queries that they're sending down. So with that, I think we've done very nicely on time. Obviously, you should have seen this in every other session you've been to, so we definitely value your feedback on the session if you'd like to provide that. Otherwise, we'll thank you for attending the session today, and if there are any final Q&A, we can take them on the mics, or you're welcome to come up and talk to us directly at the end of the session, which is right now. Thank you very much.
All right, thanks.